All right. So gradient descent and machine learning. I just, did my standard sort of thing. This is La Tech and PowerDot. So, oh, I got the wrong date. Sorry. First bug is the date. Um, okay, so this is just a sort of a background on optimization, and I actually meant to do something a little bit different here. Let me go to my source, and what I really wanted to do was turn on I want to make this the presentation. So I'm going to toggle presentation mode on. So this is how much I did not have time. Okay, so now I'm going to recompile this, and now
That's on me, Julius. I didn't say go for it until pretty late in the day today.
I was also just surprised at the time. I wasn't watching the time today.
Yeah.
What this does is just makes it kind of step so you don't get hit by a whole screen full of math right away. So let's see, let's get out of here and open it up again. Although some of them might not. I also didn't have time to go through and make sure that I put in the pause thing. Okay, there's one. All right, hold on. So it'll help a little bit at the margins. Okay, let's maximize again. Do you see the screen okay?
Got
So
it.
this is just, background. What is gradient descent? Well, so it comes from minimizing functions, right? So you have a function and it's differentiable, and so you can expand it in a Taylor expansion, and you can truncate it to the second order approximation. And so if you just keep the second order terms of the Taylor expansion, then you've got a parabolic approximation. And that is what is minimized by Newton's method. And in the case of gradient descent, you can think of it as an approximation that does not know the second derivative. So it just has to work with the first derivative. But it specializes nicely from the Newton method. So f prime is the first derivative, f double prime is the second derivative. And so hopefully everybody's seen Taylor expansion. It's a polynomial expansion. It's a polynomial approximation of a function at a point, x0. And so if we're truncating the higher order terms, then we can just solve it. Okay, we can jump to the bottom of the bowl. We approximated this thing as a parabola and about some point x0, which can be anywhere on the parabola. And so what we do then is just jump to the bottom, and the bottom is characterized by a zero gradient because there's only one point in a parabola that has a zero gradient, and that's the minimum or the maximum. And to see whether it's a minimum or maximum, we look at the sign of the second derivative. And so that's hopefully just reminding you how we minimize functions that are continuous and differentiable. And so you just write it down and solve, and you get, the jump. You get the Newton step. So the Newton step is minus the gradient divided by the Hessian, or in this single variable case, it's minus the derivative divided by the second derivative. And so that's just guiding intuition, So setting the gradient to zero means you're going to step by this amount. So if you step by this amount, you will jump to the bottom of the bowl. That's the Newton step that takes you from wherever you are, x0, anywhere on the parabola, to the point at which the gradient is zero. And so that's your basic optimization background sort of thing.
And that's all caveated on the parabolic approximation, right?
Yeah,
You,
yeah.
you jump to the bottom if the parabolic approximation is appropriate.
Well, you jump to the bottom of the parabolic approximation, whether it's a good approximation.
Okay. Yeah.
Yeah.
Fair enough. Fair enough.
We'll discover that, right? Whether it's good or bad.
Go there and see how it goes. You just look at the error again. The error hopefully the error went down.
Yeah.
You're going in the gradient descent direction, right? But you might go
Hmm.
too far. And so this normalization by the second derivative is just saying how far you should jump if it's a parabola. But if it's not a parabola, you may be jumping too far or not enough. And so that's where all the problems come from, is in how far away this is from a parabola. But if it is a parabola, then you're going to be done in one step of Newton's method.
Hmm.
Anything else about that?
So you're saying not just a parabola, but it's perfect, right? It's completely smooth. There's no discontinuities or anything with it.
Yeah, we just need differentiability. We need it to be smooth enough to have at least two derivatives. And because we use,
Okay,
yeah. So it's got to be continuous and it's got to have a first derivative and it's got to have a second derivative. But of course, you can jump around discontinuities. You can just say, well, let's move away from it and use that. But it could be completely invalid. Depends on what's going on. So, but yeah, if it's continuous and differentiable at least twice, then we can just keep doing this and hopefully converge to the answer. And one of the real pitfalls in this whole approach is if you have a broad flat minimum, if it's very flat, then the curvature goes to zero, and so the second derivative starts to go to zero, and that's very numerically unstable. So you're on this very, very flat valley floor, and this method is trying to jump you all the way across the valley to the minimum, wherever that is. But there's going to be a little error, so if there's any error at all, then you can get flung far away from the valley, and that's notorious in like polynomial root finders. So they have all sorts of guards for this. When the second derivative gets too small, you can just add a little epsilon here, right? Then you can regularize it. So it's you sort of maximize how far you're willing to go. So if you add an epsilon in the denominator here, then the second derivative can vanish, and you'll just go ticking along. You'll just fix the step size at 1 over epsilon and use the gradient to tell you which way to go. So
cool.
that's one of the that's the real pitfall in the Newton method. So the gradient descent is more robust. It doesn't have that problem. But the other thing they always say about Newton's method is that close to the solution, it converges quadratically. And so from a numerical point of view, you can think of it as doubling the number of significant digits in your solution each iteration. So if you look at quadratic convergence, it's actually doubling the precision, the number of digits of precision each step as you go into the solution, the minimum. And all reasonably smooth functions are reasonably well approximated at the solution by a parabola because they all have, vanishing higher order terms. Close to the solution for a smooth function, these higher order terms vanish, and so you're left with, this becomes a really good approximation. So everything becomes approximately quadratic if it's reasonably smooth near the solution. And so this becomes a really good model as you converge and so what's normally done is you just sort of reduce the learning rate. So you'll have like a large learning rate and you'll plateau at some sort of noise variance in the gradient. And then you start a schedule of reduced learning rates and you just kind of hone in that way. But another thing you could do is start bringing in second order estimates, start estimating curvature and normalize by that, and really get that quadratic acceleration, that Newton acceleration in the convergence. But I don't think I've seen that really in machine learning. I've seen all kinds of learning rate schedules and such, but I haven't seen people really, at least in production, do an actual Newton step where they really try to estimate the curvature or the Hessian and step that way. But I have seen it in research, so I've seen some papers in that area, but they don't seem to be, commonly used. And I was thinking Muon might be doing that, but that's not what they're doing. So we'll get to that.
Okay. Ted has his hand up there.
Yeah,
Ted.
great. Ted's here. Great.
Hey, Julius, two things real quick. So, first, just at the risk of stating the obvious, everything you've said is around the nearest minimum, but this is a local minimum, not guaranteed to be the global minimum.
Right.
And then if you if you think about it, you can see what is the dimensionality of a 7 billion parameter model? What is the dimensionality of the Hessian? And that's why people don't literally do Newton's method.
Yeah, yeah. But you could still try to estimate curvature in the gradient direction. If you had some kind of estimate of the sure, you could use it.
Yes, and I don't know if it's mathematically rooted, but if you're going to get into it, some of this stuff like Nesterov and momentum has to do with, am I going a little above or a little below my gradient? And that's not mathematically calculated, but what I've seen a lot of people write, that's the intuition is that you're not necessarily getting an accurate second derivative, but at least you're getting a sign. You're going slightly above or slightly below that first derivative.
Mm-hmm. Yeah, so a correction in that direction. Um, okay, so then I decided we should all know the perceptron, right? And the fact that it does gradient descent. And so that's an interesting derivation. So so this is all the way back to 1958. It's a single layer classifier. You can think of it as one neuron. And so this is the computation. So here's your input vector, here's your weight vector. There's only one. And then you've got your bias. And then you take the sign. So that's your crude activation function. And that's your estimate. So your states are only plus or minus one. And so you either get plus one or minus one out of this. Okay, and so in training, you try to minimize the number of misclassifications. And so here's the loss. So the loss function is the maximum of 0 and minus y, which is plus or minus 1, times, this is not a function evaluation, times this thing up here. So we've stripped away the sign. So we're doing this pre-activation, right? Except that this max with 0 gives you a kind of activation. You can actually formulate it as ReLU of minus margin, where margin is, how much it exceeds the threshold. And so when it's positive, when it's correct, then the margin is how correct it is, you could say. So ReLU of minus margin is an interpretation of this, perceptron loss. And so your labels are just plus and minus 1. So let that soak in a bit. So this is our loss function. And now we're going to be able to differentiate it and do a gradient step. So, we're way back in the 50s here. Okay, so this is our loss function. Now we can differentiate this, right? Because it's just in the derivative 0, 0. And for on this side of the threshold, then we can differentiate this with respect to w, and we'll just get x, right? Y is a fixed label, plus or minus 1. X is our input vector, and we differentiate this product, this dot product with respect to w, and we're just going to get x. And the derivative with respect to the bias, the derivative of the bias is going to go to 0. So this is very easy to differentiate, and you can see what it's going to be. It's just going to be minus y sub I x sub I. And so but if we are on this side, then we get 0. We have a little switch we have to do. Okay, so here again is the perceptron loss. And let's get the gradient. So like I said, minus y sub I x sub I if the label times the evaluation, or the pre I want to say the pre-signum activation is less than 0. So that's the misclassification. If it's classified correctly, the error is 0. Okay, so we've got a gradient, and we can now step in that direction, and it's really simple. And I think it's really important to notice that the gradient is proportional to the data, and it's proportional to the label. And usually, the label, well, in my field, the label is data as well. So it's very important intuition to know that your gradient is proportional to data. That what the gradient is telling you to do is to go in the direction of the data. Make your weights look like data. It's always adding data vectors into the weights with some, and this is normally an error. So you're normally taking the data vector, multiplying it by an error, and so that gives you a scaling of how much you need to add that, and also gives you the right direction. And so that intuition has served me well, just to think in terms of the gradient being proportional to data, and it leads you to all sorts of things like normalization. Like if you didn't normalize your data that well, well, you can normalize your gradient. And so you see in both Atom and Muon, it's just about gradient normalization, which, makes up for not having data normalization as nice as you would like it. So that's why I think Atom was a huge breakthrough because it solved the problem of inadequate data normalization by just normalizing the gradient. And Atom, as we'll see later, normalizes the gradient component-wise, whereas Muon normalizes it by just one norm, normalizes the whole gradient by the norm of the gradient. So it's a simpler thing. All right, so applying stochastic gradient descent. I don't know where the stochastic really needs to be here, but that's what I read about it. So I'm going to keep that terminology going. You get the perceptron update rule. It's just gradient descent. I guess it's stochastic when your data's random, everything's random, and the whole system is kind of a stochastic thing. But you can delete the word stochastic, and I'm happy with it. All right, so here's the update. If we've got our gradient and we choose step size eta, and gradient descent is just like Newton's method where eta will stand in for the inverse Hessian. So so we're in multivariables here. So the second derivative becomes the second derivative matrix, which is the Hessian. And so this would normally be, the Hessian inverse for a Newton step, but we don't have that. We're not willing to compute it. We don't even want to have it because we can't invert it. And like Ted was saying, it's huge. If we're doing a trillion parameters, then it's a trillion by a trillion matrix. And that's a lot of 10 to the 18th elements. Even today, NVIDIA doesn't want you to try that. Okay, so you can think of
You're
it.
gonna work the night shift at Walgreens with your brother Timmy when you grow up because y'all are both pathetic losers. Always have been, always will be. You ain't ever gonna be nothing. Just sitting up in the house reading the newspaper all day. The only one in this family that's worth anything is Dolores. That's how it's always been. That's how it always will be.
Uh-huh. And that's very important insight. We should all ponder that. Yep. But with gradient descent, we will emerge victorious. Our family will applaud. Okay, so this is the gradient step, okay? And so if it's misclassified, we don't take it because of this switching we have, then you just free run. So this is all when misclassified and when correctly classified, you just leave it alone. So that's the switching action. All right, so this is just a rephrase of that. It's known that so this will give you the perceptron update rule when it's misclassified. This is just restating it. Add the inputs, scale by the label, which is plus or minus one. And I think of that actually as error. So if it's the error would actually be two, right? Because if it should be minus one and it's two, and it's plus one, then you're going to get a two. So you can absorb that into eta if you want to think about it that way. So the high level intuition I came away with is that you just take your data vector, scale it by the error, which in this case we just use the label because that's proportional to the error, and just add it in for misclassified samples. So if it's classified correctly, the error is zero, and so that's equivalent to just skipping it because do the same thing. Okay, here's a fun thing. This is guaranteed to converge when the data are linearly separable. So you can actually prove this, and Novikov did it in 1962. And so that's really interesting to me because it's like a gradient descent with eta equals one or eta equals one half or whatever you want to, it's just some fixed, not proportional to the inverse covariance matrix. That's pretty good that is guaranteed to converge in the linearly separable case. And there's a geometric interpretation of that, which is that the updates push the decision boundary to correctly classify the data. So you can animate this. This would be a nice video using anim. Is it three blue, one brown. Oh, I don't know. You know those nice animations. That would be a very nice animation to have for this right here. Okay. Yes. So the historical note here is that the Perceptron's limitations led to the AI winter. So I remember Marvin Minsky wrote something really negative about this stuff, and Bernie Widrow at Stanford was working in this area, and then people just basically decided it wasn't going to get very far, and they just dismissed it. It was didn't have a future, right? And so, but then later, people kept going, people persisted, and somebody had the brilliant idea of making the activations differentiable so that you could do back propagation through the whole stack.
Mhm.
That is a bit of an unsung hero. I have not seen anyone get a Nobel Prize for that yet. It's a really big step forward, to think about because the signum function is not differentiable. Just taking the sign, just having a crude logistic function, but to make it soft like a tan H or all the others that we use. And Raylu's is beautiful. It's either 0 or 1 for the slope, um, and that's differentiable, and that allows you to back propagate, and you can go all the way through the layers. That plus moving it to the GPU and being able to scale, that really launched the deep learning revolution.
Yeah.
So next, let's go to Newton's method and how it connects to the perceptron, um, and then we'll go to Atom and Muon. And feel free to stop me or whatever. All right. So here's to do Newton's method in multiple dimensions, we need the multivariate Taylor series expansion. So we need to be differentiable, and we're mapping from Rn to R. So the previous version was just R1 to R1. And so now you have this. This is what your Taylor expansion looks like. And I didn't even try to write it for the higher order terms because we're going to throw them out anyway. So you got your function, and that's a scalar because that's going to be your loss function, but it's a scalar function of a vector in Rn. And then your gradient is here. And so that's going to be a vector now. And so you have a step size, which is a vector in the space. So your step size is a step vector. And so the dot product of that step size with the gradient is your, first order expansion. So the function plus that term is your first order model. That's your sort of hyperplane approximation to the function at the point x. And then if you're going to go quadratic, then you'll have this term, and that is, you can think of that as a quadratic form. And so the Hessian here is the matrix of second derivatives, and then you evaluate it with the step twice, and so that's the quadratic form. There are a lot of names for this. So this can be positive definite, and then this becomes like a Riemannian metric, and so there are various ways to think about it, but it's just a vector Taylor expansion, and here it is. And so now we can solve this the same way. Set the gradient to 0 and solve, and you get the generalization. You get Newton's method in higher dimensions. And this is just a little side note that says you can express the Hessian as the Jacobian of the gradient. So the Jacobian operator takes the derivative. It's the matrix of derivatives. And so if you get the matrix of derivatives of the gradient, that's the Hessian. And so sometimes you see it written like that. And so ultimately, though, it's just the matrix of second derivatives. And it's the Jacobian of the gradient. And so here's another way of writing it. And so this is just, the notation that you see around. Okay, so in Newton's method, we approximate f by a paraboloid, not a parabola, but a paraboloid, and we jump to the bottom of it. So it's really analogous. It's the same thing. And so what we had before was this, starting point minus derivative over second derivative at the starting point, and that gives us a new point that's hopefully the bottom of the bowl. And instead, we've got this vector version where the second derivative is the pre-multiplication by the inverse Hessian, and the first derivative has become the gradient. But otherwise, it's the same sort of thing. And the same sort of issues pertain. Okay, so that's straightforward. So each Newton step, we will minimize the local parabolic approximation. So here's a graphic for that. So we're at x0, and so the linear approximation looks like this, and then the red dashed line is the locally parabolic approximation. And so our Newton step takes us from this blue dot down to the red dot, and we use the slope of this green dotted line, which is the tangent slope here, and then we also have the curvature there that we use to find this actual step. So the derivative evaluated at this point divided by the second derivative gives us the step, and we go there, and that gives us x1. And this is the bottom of this parabolic approximation, but it is not the optimum because the original function was not a parabola. And so this is what we do. We just keep fitting parabola and jumping to the bottom, and then do that until we converge. Once it doesn't change anymore, we figure we're probably there. So that's your Newton method in 1D. And then the same sort of thing happens in 2D, where we're on some surface and we compute we do a local second order Taylor expansion to make a local paraboloid. I don't know how you make that into an adjective, but a local paraboloidic, a paraboloid approximation, and then you jump to the bottom of
There
that.
you go.
Yeah, paraboloid approximation. No IC at the end. That's the adjective operator is too unwieldy. And so
You're trying to make it too hard.
yeah. Some things are just, I don't know. I have to find out what ChatGPT wants to do with that. Make this an adjective, see what it says. And so then you just jump to the bottom of your paraboloid, and that's how you get around in higher dimensional Newton's method. So that's one Newton step, okay? And it's also a gradient step because you went in the direction of the gradient. But when you multiply it by this matrix, this positive definite matrix, that does an operation on it that essentially orthogonalizes the components of the gradient. So you can think of that operation as normalizing curvatures in all the various directions. So you can, if you go back to the one-dimensional case, what you really want to step is the gradient divided by the second derivative. So your ideal step size is 1 over the second derivative. Well, if you're trying to do a Newton step and you've got this gradient, how do you divide each component of the gradient by the second derivative? Well, you would need a diagonal matrix of second derivatives. And so if the Hessian is diagonal, that's what you'll get. So you see that the diagonal Hessian will do exactly what you want, but it will do more than that. So if your directions are not orthogonal, then you can also additionally orthogonalize. So in other words, an ellipse will be deformed into a circle, and a hyperellipse will deform into a hypersphere, and so that means the directions are orthogonal, and they don't interact, and so you can get all that from a nice Hessian matrix, a good approximation to it.
Julius, so it's just the multiplying by the, I guess, inverse of the Hessian does the orthogonalization? Is that what you're saying?
That's one of its roles. Maybe it's better to call it a normalization. So you're normalizing. Let me see. Let's go to that real quick. Let me just jump ahead to the. I want to go.
We can wait. I don't want to get you out of order. I can ask the question again later.
I might not actually get to it. It might be down here. So here's the Hessian, because I basically wanted to make a section on the Hessian, curvature, gradient covariance, and Fisher information because they're all interrelated. And so I typed this into ChatGPT 5 and said, give me a discussion. And this is the discussion it gave me. And I haven't really vetted it completely, but we can do it in real time here. So here's the definition of the Hessian. And so if you want the curvature, you take the quadratic form. So that's exactly what we need, right? Because at least that's what's in the Taylor expansion second order term. And so here we go. The eigenvalues of the Hessian measure the curvature along the orthogonalized parameter direction. So that's the sense in which it's orthogonalizing. Okay.
Okay.
So so if it's diagonal, then your eigenvalues are sitting on that diagonal. Those are the eigenvalues, and so there's your curvature, and we just take the inverse of that to normalize our gradient step. But
Hey, Julius,
yeah,
can I interrupt? Sorry. Well, I already have interrupted, but
well, I would love it if you would say this because I know you'll say it really well. So give us a
well, I just want to be careful with terminology. So if we stick to just two dimensions, which I can almost wrap my head around, okay, then the the Hessian is going to be a 2 by 2 matrix, okay, and basically when I think of the terms, basically what I think of is an ellipse, okay.
in general, it's an ellipse, right? And that's when you get
Okay,
diagonal terms, right?
so so when we diagonalize that matrix, okay, what that does is it rotates the ellipse so that its major and minor axes correspond to the x and the y, the east, west, and the north, south directions. But it doesn't, that's a separate concept from if we scale it by the eigenvalues, then it turns it into a circle. So those are two potentially completely separate steps.
Yeah, so when it's diagonal, you still have an ellipse in general. It's just that it's aligned with the major axes. So the off-diagonal terms allow it to rotate. So you can get an ellipse at any orientation.
Right.
There you go.
So so it's kind of this funny business of does it does it does it matter if the ellipse is oriented in a particular way or not? And so depending on the context, you will see sometimes people, they don't care its orientation, they just simply scale it by dividing by the eigenvalues. And then we'll get to Muon, and I'm still trying to wrap my head around exactly what's happening there.
Well, we're stepping, the components of the gradient are along the coordinate axes. So if the ellipse is aligned, then dividing by the curvatures will be exactly right in both of the component directions. But if the ellipse is rotated, then the eigenvalues, will be different. So what do you divide each component by exactly, right? Because, let's say the ellipse is at 45 degrees, then by symmetry, it needs to be the same thing, you would think, right? Because they're sort of, the X and the Y axes are sort of equally, have an equal relationship with respect to that ellipse. So you don't really get, there's no way to divide one by one eigenvalue and the other by the other eigenvalue. So you need to, so I think that's why you need to go into the orthogonalized space and then normalize and come back if you want to work in that other space. So that's my intuition on.
If you get a diagonal Hessian, then your gradients won't correctly lead you to the minimum, but the amount that they will be wrong will be only a function of their own second and additional derivatives.
Mhm.
If you have a diagonal oval, then the amount that they're wrong is going to be dependent not only on their higher derivatives, but on every other direction's higher derivatives. And one intuition is if you have a 100 million dimensional problem and how much you're off is dependent on everybody's second derivatives, then it is possible that one bad second derivative, one large second derivative, will screw up your gradient steps on all 100 million directions.
Mhm.
If you orthogonalize it, then that one bad second derivative can only mess up its own, and the other 99,999,000 will only be off by their smaller second derivatives.
Yeah, yeah. So they all get jumbled together if it's not orthogonalized. And it's weird though, because it's really kind of a rotation, right? Well, what it is a change of coordinates so that the axes of the ellipse are the axes along which the gradient components act. But it's weird to think of it as a rotation when you can't rotate really with a positive definite matrix, right? It's an orthogonal matrix that does rotations, and positive definite matrices you think of as doing dilations, but they do it along these certain axes. So I don't know. I need to think about that some more. Okay, so let's go back. Unless you have something more about that.
Sorry, unrelated. Roger, can you check the waiting room?
Oh, sorry. Yeah. Should we let him in? All right, if you insist.
Okay, so where were we here?
So,
Yeah, someone.
well, I was just going to say, I think I would like to dive in that a little deeper, but let's leave it till later.
Okay.
So just continue on.
Yeah, yeah. So, and I want to scratch around on a while. I need to just do some linear algebra to get this. I have my own questions. Okay, so here we go. This is something interesting that I just came up with today. It's one of the reasons why I didn't have time to check anything. This is the squared perceptron error because I wanted to connect the perceptron update to Newton's method, and so here's the idea. So you've got a loss function that you define as 1/2 the square of the pre-sine function error, the same one that's differentiated and minimized in the perceptron update. So I'm trying to make it look like a more normal least squares problem. And so we'll define this as the error. It's the pre-activation or pre-sine function error. And there it is, e sub I squared. And you need that because you want it to be differentiable. So and the gradient is the same as before. Um, and you can write it as minus the error times the data. And now the Hessian is easy to calculate. You just take the gradient and take the Jacobian of that. And so y sub I, no dependence. And so you differentiate this respect to w, and you're left with x transpose, and here it is. So there's your nice simple Hessian. And you can see that it's going to be positive semi-definite for sure. And that means you're going in the right direction for your gradient descent. And of course, you'll add epsilon to this in practice to make sure that it's positive definite before you try to inverse it. That's the standard stuff. And so now you have your Newton step, which is the step size. The step in the parameters is minus the inverse Hessian times the gradient of the loss with respect to the parameters W. And so here it is written out. And here it is in the form of error divided by the norm squared of the data times the data. And this is just a projection operation. You probably have seen this kind of thing before. So this normalization just comes up because your data vector is not normalized. But if you normalize it, it goes away. So the update projects the error E onto the normalized input direction x over x sub I norm.
Julius?
Yeah.
Yeah, sorry, that step where you went from the XIXIT transpose inverse, how did that turn into the norm on the right-hand side of that equation, equal sign?
Well, I think actually, I think the way to think about it is that actually this probably should be here, because the norm squared of x is xi transpose x. So for this to equal this, this transpose has to be here. And
Okay.
and so
But
work it out in more
But
detail.
that's not where the transpose is, I don't think. I think that would be a scalar. And what we have is actually a matrix. So I think the transpose is in the correct place, right?
Well, this is the Hessian, but this is not even invertible, right? This is clearly rank 1. So there's no way we can invert that. Um,
Is there even supposed to be a subscript, or is it really the full X?
ah, that would do it. That would fix it up.
So whatever the M samples, the M dimensional, M by D, whatever the
Yeah.
dimensionality is, and then you do that times transpose, and you get a D by D matrix.
Yeah, yeah, maybe that's what we have to do. Yeah. Okay. Well, so that's what it's got to be. This this was developed with Claude just minutes before the presentation today. So I would be very surprised if Claude made this mistake. I probably went in and added it into the LaTeX myself. But that's got to be the answer, that you've got all the data and it's a whole batch, or let's say it's the whole training set, and your Hessian is for one giant gradient step for the whole thing. Yeah.
So then Roger's original question, I think he's right. That last part of the formula, the the error over the norm, I don't think that's correct.
So we can't say this.
I don't think so. I think Roger's right. I think you caught that.
I didn't catch it. I just didn't understand it.
Well,
I still don't understand it.
Well, let's see. Do we want to work it out here? Let's see. I think that it's okay in principle. Let's see if we can save it. Yeah, I need to derive this myself by hand, but let's suppose this is, the sum of outer products of the data vectors. Okay, and that's going to be proportional to the Hessian. You also want to divide by the number of terms, right? So it would be the whole data matrix, and you want to normalize it by n, the number of terms in that matrix, and that will give you an average. So you're going to average these. Another thing I can do is put a capital E here and make it the expected value of this. So let's say we've got the expected value, and so now that's the proper, first order that's only an approximate gradient, but Hessian, but it's a good one. Near the solution, it's accurate. So the expected value of XX transpose.
Is it?
Well, no, that's actually the covariance of the data.
Yeah, wouldn't that just be the Hessian at that sample data point?
Yeah, it's the Hessian of
Evaluated at that data point, isn't it?
yeah, because it came from here. So if we're going to stick with
Right.
scripts, yeah. So yeah, we derived that. We talked through that. So yeah, that is the Hessian of that one component. So the gradient of the loss with respect to the omega for this one data sample, x of I. So it's only one sample.
So I can think of it as the curvature at the curvature at that point, at that sample
Yeah, yeah.
of the loss function, right?
Mm-hmm.
Okay,
Right.
so that part I thought I understood.
Now, can we do a Newton step or not? Let's see. So this is not invertible, right? This is
It's one data point, so it's rank 1.
right. So we can't write this. It's just not an option. But we can move this transpose over here, and then we'll get this. But we don't have a justification for that yet.
Is there some linear algebra thing that says the trace of when you swap the transposes will be the same or something like that?
Yeah, you can
So therefore, if you assumed that inverse was diagonalizable, then its trace would be the same as the trace of dot product scalar, but it's a scalar, so then it's just the number itself.
Yeah.
There's something like that.
Well,
Yeah. So
why is the Hessian not invertible?
because it's rank 1. It's only
The,
one.
the approximate Hessian from one data point is rank 1.
Yeah, yeah. So we can say,
Wait. Sorry if I'm asking stupid questions, just tell me to shut up. But am I think this is the gradient of the loss function
mhm.
evaluated at point I, x of I,
And
right?
then approximated, I think.
Well,
No, this
but
is
before I do that, I just have the Hessian evaluated at that point.
Yeah.
Why is that not invertible?
Because this is a rank 1 vector times a rank 1 vector transpose. So that's a rank 1 matrix. Well,
all
I
right.
don't, yeah,
Let me back up and ask, what is x sub I? Is that just a random coordinate or is that a sample?
it's a data sample.
Yeah.
Yeah. And so we have our data sample, we have our weight vector, we take the inner product, and that should be, it's trying to be plus or minus 1 correctly. Y sub I is plus or minus 1. And we either get 0 if it's correct or we get something bad if it's wrong. And so we formed the square error and we labeled the error E sub I. And now we took the gradient, and this is an exact operation.
Mhm.
And then we took the second gradient, and that's an exact operation. So this is all exact. And what's not exact is calling this a Newton step, because we can't even take a Newton step because the Newton step requires an invertible Hessian. We don't have an invertible Hessian. But what we can talk about now is the trace approximation Newton step, where we, instead of dividing by the Hessian, we divide by the trace of the Hessian,
Mhm.
and then wave our hands and get over here. So
Okay. Now I got it.
so we need to change Newton step to some other kind of, actually it might be the stochastic approximation, which I actually have slides for. Stochastic approximation basically approximates the Hessian by a diagonal. So it just puts the variances, the curvatures all along the diagonal and just uses that. But that's not actually what you see here because, well, wait. Yeah, the trace of this matrix is this. Yeah, so
Mhm.
the trace of the Hessian is the norm squared. So if that's what we're doing, so we can just say, because we can't divide by the Hessian, we'll divide by its trace, the sum of eigenvalues. Um, it's just the sum of the eigenvalues, right? And so that's the best we can do in this rank 1 case. And so that basically moves this transpose over to here, and it shows up here like this. And so then we've at least got a correct derivation. So I'm going to change this to the trace approximation Newton step.
Okay.
I give Claude a hard time, and I'm going to make sure it's training data, by reinforcement learning feedback. Let's see what else we have. So the update projects the error onto the normalized input direction. Newton's method on squared error gives the perceptron update for unit norm inputs. So that was the basic idea there, is to be able to derive a connection between Newton's method and the perceptron update. And so you got to normalize, and this is a little hand wavy still. So I'll sharpen it up for next time. How about that? And so I mean, this is just fresh off of the Claude,
Yeah.
but I thought I checked it. Well, at least I checked it in one pass. How about that? But I missed that. I missed that non-invertibility, and the fact that this is not the inverse. So oh well. Okay, so here's the step. All right, delta W is the error times the data. And this is a very important intuition, I think, which is that your gradient is the step in the weights is proportional to the area, but it's also proportional to the weight, to the data. And so this is really giving you the intuition that gradient descent power is data power. So if you want the weights to correct in a certain direction, you need to have data pushing it there. And so this has all sorts of implications in terms of convergence rate and quality of convergence, and just forcing us to really make sure that our data are complete and diverse and sort of normalized, in the sense that you don't want too much representation in one area. You want sort of an equal distribution of data energy across all kinds of situations that you care about without overrepresentation and underrepresentation. There's this sort of equality that you need because that's going to show up in how much gradient descent happened on behalf of those shapes, so to speak. So everything's shapes in the data, right? And so you want a balanced presentation of shapes so that you have a balanced influence on the weights in all possible cases without overrepresentations. In the old system identification days, we used to call it the property of being persistently exciting in any direction that you cared about. And so we were often doing things in the frequency domain. And so we needed persistent excitation in all spectral regions. So that would mean we needed data that's more or less equally represented at all frequencies. And so there are all these hacks for achieving that. And one of them is called preemphasis. It's always used in speech. And so you have a flattening of the spectrum, basically. So you flatten the spectrum of your data set so that there is equal representation for all frequencies. And then you train and you get a nice fit that is uniformly sensitive to the whole spectrum. And then on the other side, when you reconstruct, if you're going to reconstruct, if it's a classification problem, you're done. If it's a reconstruction situation, then you can now undo that preemphasis. And so very often you have low energy at high frequencies in audio, but the ear knows how to dig them out. And so your training works on the flattened spectrum. You get a nice balanced model. And then when you're reconstructing, you undo the preemphasis and move those high frequencies down low, but the ear pulls them back up. So there's a mismatch between perception and the gradient descent dynamics in that sense, or the energy sensitivities. So you have to, in a sense, take out all the scale factors that are perceptually induced in order to show something to the algorithm that is balanced so that it can get a balanced fit. And then when you evaluate it perceptually, it sounds really good. So you get a perceptually uniform fit in return for this flattening. That's what preemphasis is for. So this is, I think, where the core intuition comes from.
And that was spectral balancing of the data then.
Right, exactly.
Right?
Yeah. So you pre-filter the data to whiten it. And that also comes up in just pure least squares. So when you're doing least squares and you want to show that it's optimal, you can prove that it's optimal for example, data in white noise. And then when you have non-white noise, then you can make it optimal by pre-filtering to essentially whiten the noise. So if you flatten the noise, then it'll turn an arbitrary distribution into a flat distribution if that's an invertible transformation. So you want to pre-whiten your error. You want to pre-filter your error to make it a white noise, and then do your least squares. And then if you want to put back the filtering, you can. And in a reconstruction, you will.
And so in that case, then the white noise, so the updates to the weight is driven by the data. If your data is white, then it's kind of white updates into the weights.
Right. Yeah.
And
So
that's going to be numerically optimal.
it means that your weights are being equally updated at all frequencies.
Uh,
So it means that the low frequencies are getting updated a certain amount each step, and the high frequencies are getting updated the same amount each step, because there's an equal representation on average across data samples. So the total data energy is the same in every frequency band, and that allows you to converge. And I actually was watching a talk by the guy who did the movie gen stuff for Facebook. He gave a talk at Stanford, and I was there, and I think it was CS25 lecture. I think it's on YouTube. You can find it. And he was saying that they do a lot of normalization, and it sounded like it was this idea that that you want to analyze your data, cluster it, and normalize it. You don't want, really heavily populated clusters and then have, very thinly populated clusters. You want to try to get kind of an equal population across all clusters, and then and then get a nice well generalized model from all that. And I don't know if that really connects, but it sounded like it did.
Could you tie that into like using diffusion for training? That it is getting that full spectrum image data, right?
Yeah, I mean, it's going from white noise to the distribution you want.
Right. Right.
Mm-hmm. That makes sense.
Hmm.
Yeah, that gets us into gradient flows and diffusion. Yeah, we can have a whole night on that connection. Gradient flows versus data flows, right? So this is parameter gradient flow, and then diffusion is like data parameter data distribution flow. It's kind of they're sort of dual in some sense.
Yeah, well, it kind of addresses, your point of you get to train the model on not just your sample points, but lots of points throughout space, right? Because of the diffusion, you just keep adding the noise.
Mhm.
And so I was just thinking, does that balance into your idea of training, again, not just the data points, but more samples?
Well, it makes
Full spectrum kind of.
it makes sense to me that when you add noise in the diffusion step in the diffusion progression, you're adding noise and then learning how to undo that noise, and
Yeah,
uh, that training is going to be uniformly uh, it's going to have uniform energy across the spectrum because
right.
white noise.
Of
So
images. Yeah.
yeah, and anything you're working with, yeah, that makes a lot of sense. So you're adding the white noise, so you get this property for free that you have the persistent excitation property for your data. And in this case, the data is the noise. You're trying to undo that. So you're trying to learn how to cancel it.
Hmm. Hmm.
So it's uniformly distributed across the band. So you're going to get this property. Unlike, when you're just working with data from the wild and you don't get that property with probability one. So that's a real nice advantage of the diffusion formulation.
Yeah. Yeah.
Cool.
Hey, hey, Julius.
Yeah, Ted.
I'm 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 trying to follow your conversation, and I think I maybe got lost a little bit. When we talk about the derivatives and the partial derivatives, originally you were talking about this function L is well, it's a function of x or whatever. But the partial derivatives we're taking are actually with respect to the parameters. So we're taking the partial derivatives with respect to w, not with respect to x.
Right. Yeah. So that's parameter gradient flow as opposed to um, data distribution gradient flow, score function flow. So yeah, in some sense, that's the sense in which I feel like they're duals, right? So you're in one case your your flow is the gradient flow for the weights. That would be, this. And then the other case, it's the gradient flow for the data. You're pushing the data distribution from, Gaussian to what you want. Yeah, I feel like there's a whole talk on the duality of diffusion and stochastic gradient descent.
But when we talk about the gradients, the Newton step,
The trace approximation Newton step. Maybe get to something that's correct and show that. This I think I believe in this. I don't hear anything. Is anybody
but
Sorry, we're thinking? Okay.
My
so
gears are grinding.
so when we talk about taking a Newton step, okay, we're talking about taking in the case of training models, we're talking about taking a Newton step on the weights. So your X's here are actually representing weights, not data of your model.
That's right. That's right. But the gradient is proportional to data, right? That's the point. So even, yeah, we are stepping the weights, but the step size is proportional to the error and it's proportional to the data.
It's not. It's proportional to the weight. X sub 0 is a weight now.
Um,
Because we're talking about
Right, Sam?
optimizing in weight space.
well, we're optimizing in weight space, but the derivative just turns out to be proportional to the data. So here's the error, okay? And it's the weight, the dot product of the weights with the data. And because we differentiate with respect to the weights, because we're stepping in weight space, all that's left is the data. The derivative of the inner product of the weight and the data is the data.
Yes, the magnitude is proportional, but the direction is with respect to the weight.
Well, the derivative is with
Not
respect,
into the weights. To update the weights, you're going to use the data.
right.
To propagate into the previous into the input, you're going to use the weights.
That's right. So the data is the weights are a big pile of data. It's and this goes back to the original perception state. You know, you take your data and multiply by plus minus one if it's a perceptron and just add it in, throw it in there. Just keep adding up the data, but it's the incorrect data, right? If it's correct, then you add in zeros just because that's the error is zero. But if you've got an error, then you add it in. So your weight vector is just an accumulation of data.
Accumulation of transformed data.
Well, scaled by error data. But no, it's actual data. Because you know you're adding up a
Well,
bunch.
for single perceptron, maybe it's
Well, this is a general thing. Let me go back to the general. Well, I want it in the notation that we need. Um, see, is that correct? Let me see if I
I
can.
mean, your data and your weights are different dimensionality, right? So there has to be a projection of some sort.
Oh, and the weights and the data are in the same space. Yeah, W
No,
and X are in the same space. You got to be able to take an inner product of them. So your weights, you know that funny trellis diagram that everybody draws. That's just the matrix multiply, right? And then for one neuron, it's the weight vector transposed times the input vector. And
no, but the weights are rectangular. Y is multidimensional and X is multidimensional.
well, weights have been are one vector, so it's a one tall skinny rectangle. Are you thinking of a whole matrix?
That's only
There's
if you
a
have a scalar Y.
Yes, y is scalar here. Y is a scalar. It's the only scalar. And so there's no underbar under it, right? So all the others are n vectors, Rn. And so the weight vector, which is an n by one, I think of it as a column vector, n by one, it gets a scalar y, which is plus or minus one for the perceptron, times your data vector, which can be just any bit pattern, right? But it's capital N. They're in the same space. But you can see that the weights are just it's just a pile of data vectors. It's just a sum of data vectors where each one got scaled by the error. And in the case of a perceptron, the error is either zero or the actual desired value. It just kind of works out that way. And you could argue there's a factor of two there. So that is an important intuition that the weight vector is just a big pile of data. Here's a case where it comes up for me where I'm trying to learn a sinusoidal weight vector shape. I'm trying to make a sinusoid predictor where when I take an inner product of the of the sinusoid with the weight vector, I just continue the sinusoid. So it's like a sine wave predictor kind of a thing. So I want the weight vector to look like a sine wave because that would give me a maximum dot product. And you got to shift a sample, but that's a second order thing. So I need the weight vector to look like a sine wave. And that's what's going to happen because when I have an error, I'm going to take the sine wave that I want and add it to the weight vector. So over time, it's going to look more and more like the sine wave I'm trying to predict. Until the error goes to zero. Once I'm nailing it, then this goes to zero and I just leave it alone. So I'm going to learn the sinusoidal weight vector that will dot with the current state of the sinusoid and produce the next point of the sinusoid. So it's a sinusoidal predictor. It's a linear predictor, you could say. So that's the whole linear prediction story.
So in this case, the perceptron, these equations are for the perceptron. This is going to be a kind of a flat, in the way we think of the weights and hidden states now. This is going to be just a flat single output network, right?
Yeah, it's one neuron, one neuron.
One neuron. Yeah. Okay. And that's why W and X are in our same dimensionality.
Yeah, yeah.
Okay. Because Y is scalar.
Yes.
And W and X are
They're
same
both
dimension. Yeah, same
a
dimensionality.
bunch of X. So Y is just your sample index, right?
Okay. So when we get later on to X, Y and X both being vectors or tensors and weight being a square matrix, then there's another discussion that I'd like to kind of go through to understand
Yeah.
this, because I think you could make the same statement about the weights being the sum of the data, the input data.
Yes.
But I think it requires a transformation is all. You have to project X into the weight space.
And well, the way I think about it is you take all of your weights from all of your layers and just put them in a giant long list. That's your weight space, right? And your gradient's in that space, right? Your gradient is just this long strung out thing that corresponds.
But you can't do that anymore because now you actually have interaction between the terms. It's no longer just linear.
Right, right. Yeah. So the gradient, that's where so you got all this back propagation to calculate. But still, once you get through all that back propagation, every weight component gets updated by its gradient. And it only depends on, the number of layers to the end from where it is. But at the very beginning of the network,
Right. But its gradient is no longer just the data because now it's mediated by
Oh,
all
higher
the other
level
weights
weight.
in its
Yeah.
layer,
Yeah.
not just itself. So I can see how the single perceptron is I'm still not well. Do you initialize a perceptron or?
I don't know. This is how much I prepared the perceptron stuff right before. I didn't even realize it was so late, but I shouldn't have done this at all because I should have been checking my other stuff instead of trying to
All right.
squeeze this in. I didn't really review anything. This is all I have.
So
No,
I'll
but
just throw out.
I think it's good insights, and I think the insights carry through.
Yeah, we can find them, so we'll work on that. But I am speaking from experience when I say that the data have a big impact on the convergence of the weights, and that data
Yes.
normalization really helps. The gradient descent uniformly converge to a good model for all the data if everything's balanced. And so I'm sure that story does generalize, but we have to work out the details. And here it's clear in one layer or one neuron even, and that would go to a whole layer because a layer is just a parallel bank of single neurons, and there's no interaction between them of this nature. So the gradient does go in parallel into all of the neurons at one layer. So that's okay. So we're doing the one layer case precisely. But yeah, we got to look at the activation and the differentiation and whatever nonlinear functions are there, and what it looks like going back through an activation and back propagation.
Yeah. In more simple terms, one of the things you had talked about with like this whitening, I was trying to think about because when we do linear regression, we typically will scale the data. We may reshape the data, right? So an old adage is, right, you want your data to be normally distributed. And I was just trying to figure out whether that's a direct or an indirect thing. Do we want the data to be distributed this way because we want the data to be distributed this way? Or do we want the data to be distributed because that will help our errors to be distributed a certain way? The maximum likelihood assumption for linear regression assumes Gaussian error distribution. So I was just trying to wrap my head around, well, are we shaping the data to get the errors to look a certain way, or are we shaping it just literally because we want the error, the data a certain way? And I wasn't sure which of the two is the primary reason.
Well, I know that certain interpretations assume Gaussian. So if you want to talk about maximum likelihood and you want softmax to be really valid and that sort of thing, then yeah, that could make a lot of that could be a reason to want that.
Right. So my understanding is no matter how your data is distributed, if your errors are distributed Gaussian, then linear regression will give you the exact maximum likelihood estimate. The
least squares solution.
The least square solution will give you the maximum likelihood estimate.
Yeah.
The only requirement for that is that the noise be Gaussian, not that the data be distributed in any particular way.
Yeah, that's the beauty of maximum likelihood. It doesn't matter what your parameters are, what your machinery is that go from your parameter to your distribution, as long as the error is a Gaussian white noise, then you're golden. And you can whiten it if it's not white. But even if it's not Gaussian, you can still call it minimum variance, and that's sort of the next step. But yeah, to get all the nice theoretical properties, you want Gaussian. Boy, that's way back in my memory.
So we are approaching time.
Well, I guess
and so
we can wrap up the perceptron and Newton, because the next topic was Gaussian least squares and recursive. So this is the stuff that I worked on. And then the stochastic approximation just does a diagonal approximation to the Hessian, and that's used, and that sort of takes you to atom and then muon. And so that was what I had. So we almost made it, but we didn't quite get out of the perceptron.
if we can do atom and muon next week, I think that would be great.
Okay.
Yeah.
Sounds good. And then
all right.
We'll still have more than enough, because if we run out of time, well, we can talk about best practices, with all of our various software environments. And I've also got a lot of, I'm sure I can fill up the available space with Hessian, loss curvature, gradient covariance, Fisher information. And I have what I love, I have a derivation of the univariate guess, the log likelihood, and the Fisher information. It's all really simple in the case of a Gaussian. So if you have known mean, unknown variance, unknown mean, known unknown variance, so it just is really pretty and simple. And so if anybody's interested in the fundamentals of maximum likelihood and Hessian and curvature and Fisher information, we can talk about that.
Definitely.
All right, I think we're done for tonight, though, right?
Did you say there was one left? Perceptron versus Newton update? Was that?
Well, this is it. This is the last slide right here.
Okay.
So
have we done this one? We haven't done this one yet. So
yeah, so here's our perceptron update, right? So the weight update is the error, which is plus or minus 1, times the pattern you're going for. And then the Newton step uses the same error without the sine function. And then if you normalize it, it becomes, analogous to the perceptron update. So we have to normalize the inputs to get the norm squared to be 1. And then the weight update becomes the same error as in the perceptron times the data. And so you can say that this is valid near the decision boundary because far away from the decision boundary, you've got the sign function changing things. So this will recover the perceptron update for samples close to the hyperplane that divides classes. And if it's badly misclassified, where you've got, you're just way off, then you can RMS normalize the weights, and then you can show then that your weight update looks like this, which is effectively twice the usual perceptron update. So, and I'm going to credit Claude for this. Claude suggested this. I'm just checking Claude here. This is Claude 1, and we had this conversation literally minutes before 6:30. I had no idea how late it was getting, and so here's Claude's conjecture here. I think it's probably right that Newton with normalization is an adaptive perceptron with the step size eta in the set of the interval 1 to 2 based on confidence. So if you're close to the hyperplane, you slow down. If you're far away, you speed up. So that's I think that's a beautiful thing. I think Claude's doing research here. I think we've AGI. This is a little scrap of AGI for you.
Yeah. Well, will it be graduating next year at Stanford? Will you be handing it its diploma?
Oh, I'm so glad I don't have to decide that. Can you imagine? Can you imagine, being so what do you do now, if you're having to grade people and it's like open world, open LLM. So they're using all hands-on and they give you some stream of BS and you have to check it. So I don't know. I guess I have to pay big bucks and get access to some really hyper powerful
Yep.
AGI super AI behind the doors of OpenAI or Anthropic, work out some deal. Stanford has to work out some deal.
Yeah. Yeah, but then next year it'll be superseded, right? So the next semester it'll be useless.
Yeah, as long as the models behind closed doors are an order of magnitude smarter than what's out there, you can use them to check, right? You can use them
Right.
to grade everybody. And I'm assuming they've got these, super high powered models that they're not releasing because they're very expensive, right? But they use them to distill and to, to student teacher and generate training data. And there's all sorts of things you can do behind the scenes with a super powered model. It's very expensive to put out what the rest of us use. And so educators are going to need access to that. And maybe a lot of other people do too. So because we're not going to do that, right? I mean, so here's my algorithm. I don't have to do it because I'm retired, but my algorithm is it's open world, open everything. And so I want to talk to you afterwards. In other words, put together anything you want. I read it, I understand it, and we get together on Zoom or wherever, and we talk about it. And all I'm testing is, do you understand what you turned in? And that's it. We're just going to talk about all these points. And I should get I dropped from an A to a B when that, transpose thing came out. What are you inverting? What's this rank 1 Hessian that you're inverting? And how is that, so, I should probably be flunked for that and go back to the, I have to take this class over again. But my only defense is I ran out of time. I slept through the exam, so sorry.
I'm sure your students have done the same thing to you before.
Oh yeah. Everybody makes mistakes.
Yeah.
We are now
I don't
going to
think-
give you 1 week to rework your answers.
Thank you. That's what I need. So I will try to come up with a really compelling story that makes that really sound good, and I'm going to make Claude do it with me. I'm going to give it a hard time. So I'm going to say, hey, wait a minute, because this is really its turned in work that I just passed through as a.
Oh, you're plagiarizing now.
Well, no, it was an open world exam.
Okay.
I'm expected to use it, but I'm also expected to understand it, right? I'm supposed to take some time.
You're now Claude's supervisor, right? And you're going to take credit for their work.
Oh yes, that's right. Claude
Okay.
is my new neocortex add-on layer.
The final layer.
Part of my brain. I'm responsible for what comes out of my neocortex, even when it's extended by Claude. So that's the deal. You're responsible for what comes out of your brain.
As long as you take responsibility, I guess it's okay.
Yeah, yeah, you got to have a person responsible. Somebody's got to sign off, and they have to come up with how are they going to check? How are they going to test and double check? I mean, I could have given that proof to ChatGPT 5 and it would have probably caught the error right away.
Yeah,
Gemini,
you can't, it's an old system. So I think the old perspective as far as like people versus people or people versus AI, where AI is already better than humans in many cases, is
yeah,
a system that people haven't moved on from. And you really have to look at AI as like this is a tool to build something that's never been built before.
right.
And how well can students
Good
use
point,
various
Kevin.
forms of AI to outshine other people? But like when I see this like MIT stuff of like people's brains not being activated, you can't have the same level of task that AI is doing versus the human and expect the human to be engaged. But you can get full engagement with humans as you use better and better types of AI to solve bigger and bigger problems that have never been solved before.